Alright, welcome. Today in this video we're going to talk about the second kind of differential equations that you're going to learn how to solve. We're going to talk about exact equations. Exact equations are actually first order equations as well, not necessarily linear, they can be non-linear. And exact equations, what I wrote here, is when the equation is actually the differential of a function equated to 0. So to understand what that phrase means, first we need to recall what is the differential of a function. And when we recall what differential of a function is, then we will talk about something called Schwarz theorem, which is related with that little thing that I mentioned in the classification of differential equations of the cross-partial derivatives coinciding. All right, so let's get to it. All right, so let's recall from your first year, well, from your previous, not first year, from the previous calculus courses. You remember what the differential of a function is with a single variable. So you have an f of x, right? And you can write the differential of a function as the variation of f with respect to x times the differential of the variable. Again, geometrically, if you think physics-wise a little bit, this is like, okay, how much does the function increase when I increase a little bit the variable? And that is related to the slope of the function, right? When we have a multivariable function, consider now an f of xy, then you will also remember from your previous calculus courses that we can write the differential of this function as the partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy. That is the differential of a function of two variables. Now, the differential of a function of two variables, df dx, df dy, right? It's kind of geometrically similar. How much does the function increase? If I increase a little bit x and I increase a little bit y, well, if you move in the direction of y, you increase by the slope of the direction of y. If you move a little bit in the direction of x, you increase a little bit in the direction of x. So nothing extremely difficult, I hope. Things that you've seen before in previous courses. All right, so let's talk about Schwarz theorem. So let me call this the thing. So df, these things, the partial derivatives of the function with respect to x and with respect to y, are themselves functions of x and y, right? So you get, so this thing we can call, let's use the same notation as here, px, I use t here, well, pxy, all right? I use t in this, in the notes, but it doesn't matter. I mean, t or y, t or x doesn't really matter. And this one I'm going to call q of xy. All right. Now, Schwarz theorem tells us that if f of xy is what we call class 2, what does that mean? That means that the second derivatives exist and are continuous. So the function is continuous, the derivatives are continuous, the second derivatives are continuous. Not too important to solve exercises, just to know. Then that, I'm summarizing a lot the theorem, then the partial derivative of f with respect to x first and then with respect to y would be equal to the partial derivative of f with respect to y first and then with respect to x. So the second partial derivatives coincide. Doesn't matter what order you are. So those are the most common functions that you've been seeing. You rarely have seen discontinuous functions like that. It has discontinuous derivatives. Now, that means if we wrote in this language, this means this is the same thing as saying that, right, p, the partial derivative of f, let's just write it here, dy dx is first x then y, so this thing is partial derivative of p with respect to y, okay? This is what you get when you take the derivative, the second derivative of f with respect to x first and then y. And then the second derivative of f with respect to first y and then x, then this is the derivative of q with respect to x, right? Basically because q is the derivative. So maybe I can write one more step to make it clearer. This is the same as partial derivative with respect to y of partial derivative of f with respect to x, and that thing is what we call p, right? So this is partial derivative of p with respect to y, and then this thing is partial derivative of x, partial derivative of f with respect to y, which is what we call q. So this is partial derivative of q with respect to x. Now, we know that if there is a function, so here's the key point, if there is a function, a nice enough function, such that p and q are the partial derivatives of f, that means if there is a function such that p and q form the differential of the function, then it has to be true that these two things are equal because of Cauchy-Schwarz, right? Sorry, or because of Schwarz theorem, my bad. Schwarz theorem tells us that these two things have to be equal. Alright? Now, if I give you some random, I ask you, imagine I give you a differential form like this, which is some combination of dx and dy. I give you this, imagine x squared dx plus y x dy. Imagine I give you that, and then I ask you, is that the differential of a function? So my question is this thing the differential of a function? Then your answer would be, let's check. So this is P, this is what we call P, right? This is what we call Q, and we have to check that P, this is, if this is a function, then P is the partial derivative of that function with respect to x, and Q should be the partial derivative of a function with respect to y, just comparing the form of the differential of the function. But if that is true, then Cauchy-Schwarz tells me that, so if there is an f such that df is equal to p dx plus q dy, then it has to be satisfied that partial p dy, partial y, has to be equal to partial q dx because of Schwarz theorem. Now we can check in this particular example, and in this particular example, if I erase this, we see that in this particular example, p is x squared, so partial p, partial y is 0, and then q is, what is q? Yx, so partial q, partial x is y. Oh, they are different, therefore x squared dx plus yx dy is not the differential of a function f. Okay? So this is a case where it is not true that this thing is the differential of a function. That clear? Because to be a differential of a function means that, and that means through Schwarz theorem that the partial derivative of p with respect to y has to coincide with the partial derivative of q with respect to x. And in this example, we see they don't. So this example in particular, we can ask the same question. Is this the differential of a function? That is there an f of xy? I'll write it. Is there an f of xy such that the f is equal to xy dx plus x squared over 2 dy? So that's the question I'm asking. Well, let's see. This is p in this case, this is q in this case, and we know that if there is a function, then partial p, partial y has to be equal to partial q, partial x. Alright, let's write it in this case. In this case, p is xy. That means that partial p, partial y is equal to x. And then q is x squared divided by 2, which means that partial q, partial x, is equal to x. Nice, they coincide. So, because they coincide, that means that yes, the answer is yes. There is a function f of x, y, such that this is the differential of it. Now, the next step would be finding the function. So what would be that function? That we will do, I mean, we can actually do it, but let me erase the board and let's do this particular example. Let's find the function. So just a second. So I moved the differential form up there. So we already determined that there is an f such that this is the differential of the function because the cross derivatives of the function coincide. Now the next question is, well, okay, we already know there is a function, so there is a function f of xy that satisfies that. So now that satisfies equation 1, and this is my equation 1. Now the question is, what is that function? All right, we know, remember, that the differential of a function is partial f partial x dx plus partial f partial y dy, right? So that we know. Now, knowing that, it's very easy, well, it's easy to determine, to relate the two and know, partial f partial x is equal to xy, and then partial f partial y is equal to x squared divided by 2, right? Easy peasy. So, the way to proceed, let me tell you first what not to do, because some students do this and it's really bad. They say, oh, differential here, I integrate on the left and I get f, and I integrate here and I integrate here. Very wrong. That way, sometimes it will coincide by chance, but most of the times that would be wrong because that's not the way to do it, okay? So let me tell you the way to do it. We know by comparison that the partial derivative of f with respect to x is xy, and we know that the partial derivative of f with respect to y is x squared divided by 2. Nice. Let's integrate the two independently. So here I integrate with respect to x, and then I know that integrating with respect to x, I get, well, I'll write it, the integral, so f of xy is equal to the integral xy dx. dy comes out, and we get x squared y divided by 2. Now, this is not quite f, right? It is not quite f. Why? Because this is just the partial derivative of x. If there were factors in f that do not depend on x but depend on y, we would not see them, right? Those factors would be killed by the partial derivative with respect to x. So there might be a constant here, but this constant may depend on y. Let's call it h. So let's see if we follow the reasoning. Now, because if this is a function such that if I take the partial derivative with respect to x, I get xy. That is correct. But if I add plus any function of y, if I take the partial derivative of this with respect to x, the derivative with respect to x kills this bit. So the constant that I have here is not really a constant. It's a constant with respect to x only, because that's not a total derivative, it's a partial derivative. Therefore, this thing can depend on y. The same goes for the other one. For the other one, integrating with respect to the y, we know that f of xy is equal to x squared divided by 2 dy. That's very easy because there's no y, so this is x squared y divided by 2. And again, if there was a function of x, the partial derivative with respect to y would have killed it, so the integration constant, if you want here, is a function of only x. Right, now we know that these two things have to be equal, so we see that h of y and g of x, we can get it by comparison. If there's a function of x in here, it should be here, but there's not. So this thing is 0, there's no function of x, so g of x, by comparison, g of x is 0. And h of y is also 0, because if there's a function of y only, it should appear in here when I integrate with y. So h of y in this particular case is all really simple, is 0. So the final solution is that f of xy is actually equal to x squared y divided by 2 plus an integration constant, of course, always, because if I take the differential, partial derivatives also kill the constant. So this would be the function whose, or the family of functions, if you want, whose differential is this expression. All right. All right. I hope that this is not always, as we will see more examples. This is the simplest case, that the constants, if you want the part to depend on the other variable 0. This is not going to be the case always, as we will see in an example. All right. Hopefully we understand now differential forms and differentials of two variable functions, and how to check if I give you a random differential form like this, to check if it's true that is a differential of a function. That's Schwarz theorem, comparing the cross derivatives. And then once you've checked it, you can find the f. And to find the f, you get the partial derivative with respect to x integrated with respect to x, partial derivative with respect to y with respect to y, compare the two to find the constants, the functions of the other variable, and then find the solution. Now you may be wondering, why? In what way is this related to differential equations? Well, let me show you. Imagine I give you a differential equation typically in the following form. All right. So we have, imagine I give you the following equation. Y dot is equal to minus 3t squared plus 60y squared divided by 60 squared y plus 4y cubed. Now, this is a difficult equation. Let's classify it. Independent variable, t. Dependent variable, y. Okay, linear or non-linear? Certainly non-linear. So in general, difficult, right? So because it's non-linear. All right. Well, it's an ODE, of course. All right, only one independent variable. So how do we solve it? Well, let's see. The thing is dy dt equals to minus 3t squared plus, t squared plus 60y squared divided by 60 squared y plus 4y cubed. Now, operating with the differentials or multiplying by telling your mathematician friends not to look, of course, this is the non-rigorous way, then you can check that this thing is, all right, awesome. So I have 6t squared y plus 4y cubed. That thing multiplies dy, right? It's this times that, if you want, plus 3t squared plus 6ty squared dt equals 0. You see what I mean? What I did is this times this equals this times that, and I put everything on the left. It's a minus sign that makes everything positive. Right. So this differential equation, I can write like a differential form. You see? Equate to 0. So my question is, so this would be our p, and this would be our q. Yeah, before we had an x and we had a t, but you are already good enough to know that that's the independent variable, and we don't care if you call it t or x or what. So this looks a whole lot like a differential form. So the question is, would we be lucky enough to find an f such that this is the differential of it? So is this equation, let's call this 1, and let's ask the question, is 1 a df equated to 0? Because if it is, you see, if this is the differential, and the question is this whole thing a df? We are asking, is that a df? Because if it's a df, solving the equation is easy. I can integrate both sides, and I get that f of yt equals to 0 is the solution to my differential equation. So if I'm able to find an f so that this is the differential, then finding the f is solving the equation, as we will see. So if you're asked, give the general solution to this equation, the first thing that you should do is to try to check if it's a differential form, an exact differential form. Which means exact differential form means that it's the differential of a function. All right, let's check. How can we check? Well, Schwarz, right? Let's try this. First, check for exactness. exactness. So the answer is plus. Check. All right. What does that mean? Well, that means that this thing, partial with respect to x, should be equal to this thing, partial with respect, with respect to t, should be equal to this thing, partial with respect to y. Because again, this is already, this is a differential form, this is the derivative, so maybe let me write it here. This is p and this is q, and if there is an f, we know that df would be partial f, partial y, dy plus partial f, partial t, dt, and this would be p and this would be q, right? If there is an f, which we don't know, we need to check. So checking for exactness, we have this condition, let's check it. On the one hand, we have that partial p, partial t is, well, let's write it, partial of 6t squared y plus 4y cubed with respect to t, and that thing is 12t, oops, I'll write it here, 12ty. All right, now let's check partial q, partial y, and that is partial of 3t squared plus 6ty squared with respect to y. And if we do that partial derivative, first one is 0, of course, the second one gives me 12ty. Nice. It coincides. It's an exact equation. So this equation, let's call this equation 2, or equation 0 if you want, because it came first. So 0 is an exact differential equation. Wonderful. So now that we check that it's exact, that we know that this thing is no longer a question, it is a df, sorry, then let's find out that f to solve the differential equation, shall we? Let me erase. So we have that differential of the function df is p dy, but we also know that p is the partial derivative of f with respect to y. So we write first partial f, partial y is in this case p, which is 6t squared y plus 4y cubed. All right, on the other hand, we know that partial f, partial t is the cube, which is 3t squared plus 6ty squared. All right, now we find f by integrating. Here we integrate with respect to y, and we get that f of t, yt, I don't care. What did I write? I don't care. So t, let's do ty. F of ty, it's equal to, let me erase this tiny bit. By integration, well, let's write it. The integral of 6t squared y plus 4y cubed dy. All right, we do that and we get that this thing is 3t squared y squared. Right, plus y to the power of 4. But again, remember that there can be an integration constant, but because this came from a partial derivative with respect to y, that constant is not really a constant, it can depend on t. So there's an h of t in there. Okay, so here we integrate with respect to x, sorry, with respect to t, and that means that f of ty would be the integral of the partial derivative of f with respect to t, which is 3t squared plus 6ty squared dt. And if we integrate that, we get first a t cubed, and then we get plus 3t squared y squared. And again, then we may be forgetting something because this thing killed all the factors of y, so the integration constant here could be a function of y. Now, let's identify the functions. In this case, it's super easy. All right, there is a function of t missing, of only t missing here, but not here. What could it be? Well, h of t is t cubed, right? Now, there is a function, there is a function of only y that is not here, but is here. What could it be? It would be, this is a bad one. Let's try green, even though green may be less visible, but I think it should be fine for this. Y is this one. Okay, awesome. So we've guessed the form of the function. Of course, this is the same. You will always have the same in both. So that means that I can write finally f of tx, of ty, sorry, it's equal to 3t squared y squared plus the two functions y to the power of 4 plus h of t, that is t cubed, plus t cubed. All right? Of course, plus a constant if you want. So this thing, if you want, plus a constant, but let's not write the constant, we'll put it there in the final solution. But of course, there could be also constant factors. This is one solution for sure. Now, remember what we had. So, because this is an f that integrates the differential form, we know that my equation, remember, going back to the equation now to solve the equation, equation 0 is of the form df equals 0, where f is that one. So, if we integrate this, we get that the solution is f of t y equals, and here I put the constant. All right, I could put it here, but I decided to put it here. We're integrating this one. I can put it wherever I want. Awesome. So let's write the solution to the exercise. The solution to the exercise, I'm going to write here f of t. Sorry. The solution to the exercise. The solution in implicit form is, and I can write it here, 3t squared y squared plus y to the 4 plus t cubed equals a constant. That is the solution in implicit form. Now, this will get you most of the marks if you get there. Of course, the most satisfying solution is when you can actually solve for y. What we want is a y of t, not some relation between y and t. I mean, sometimes we don't know how to solve that because it's a transcendent equation, but sometimes we do how to solve it, and when we do know how to solve it, we want to provide the form. So that will give you all the marks except for one. You will get 1 mark off if you actually don't take the next step, because this one we can solve for y. Let's do it. Let me erase the board and move the solution up there, and let's solve finally the exercise. So, okay? All right. So we move the equation up there. Now, what kind of equation is this? Well, that looks a lot like a biquadratic equation. What does that mean? If I make the change y squared equals z, all right, then I know that, of course, y would be the plus minus the square root of z, but with that substitution, this thing gets transformed into z squared plus 3t squared z plus t cubed minus c equals 0. So this is a quadratic equation. I can use the quadratic formula, and if I use it, the final solution is, I'll write here, y of t, it's equal to plus minus square root of minus 3t squared plus minus root of 9t to the 4 minus 4t cubed minus c divided by 2. And that would be the final solution to the differential equation. Well, if you don't do that one, you won't lose many marks. But it's one step. Whenever you can solve for y, again, not always you'll be able to solve for y, but when you can, like if it's a quadratic equation or something like a quadratic equation, please do solve it. All right, so this is how you solve exact equations. I'll give you just a series of rules of how to approach exact equations. It's very systematic. First, check for exactness. That means write the equation in this form, go one of the coefficients p, the other q, I don't care which one. Again, p and q are placeholders. But then check that the cross derivatives coincide. So this one is the derivative with respect to x of the suspected function. So the derivative of p with respect to t, to the one that is not multiplying, should be equal to the derivative of q with respect to the one that is not multiplying. Okay, this is checked for exactness. So that's condition one. Second, if the equation is exact, so then what you have to do is find f of xt by integrating the partial derivatives. Remember, you have this equation, partial f with respect to x equals p, partial f with respect to t equals q, and then integrate each one with respect to the variable it's taking the derivative. Remembering that you will get extra functions, you will get whatever you get integrated here, plus an indeterminate function of t. Here, you will get whatever you get integrated here, plus an indeterminate factor of x. And you need to compare the two to determine them. All right. That will actually give you the solution in the form of f of xt equals constant. And that would be the implicit solution. Implicit solution. All right. Then one final step, solve for x of t if you can isolate one of the variables when possible. Not always will be possible, but when it is, please do it. So those are the steps to solve exact equations. So the last thing that I'm going to do in this video is to solve another example of an exact equation. All right, let me erase the board. Okay, we're going to solve this example. So if you have an equation like that, it does look like perhaps this is an exact equation. So let's see, first step. Check for exactness, which is the same as saying, is there an f of xy such that equation 1 is the df of some function equated to 0? So that's the question we ask. Well, let's see. Let's write this explicitly as a differential form. So we operate with differential, or equivalently, but not telling mathematicians not to look. We say this times this equals this times that, and put everything on the same side. Anyway, this is just a mnemotechnic technique. So 2y plus x squared plus 1 multiplying dy plus 2x y minus 9x squared multiplying dx. We call one p and one y, for example. Let's call this one p and let's call this one q. All right, is that what I did in the notes usually? The most common one. It's pretty arbitrary, but yes, that's what I did. I did the p with the x and the q with the y. Let's try to stick with that convention. But again, it's just arbitrary, and sometimes the variables are called something different, so don't worry too much as long as you're consistent. All right, so is this thing, of course, equals 0? Is this thing the differential of a function? Well, we need to check for exactness, which means, all right, does the partial derivative of q with respect to x equals the partial derivative of p with respect to y? Yeah, remember, derivative of this one with respect to the other one that is not multiplying, derivative of this one with respect to the other one that's not multiplying. Let's check. So, let's compute here, partial q, partial x, it's equal, that nothing, that's 2x, and that nothing, and partial p, partial y, it's equal to 2x for the first one and nothing for the second one. Nice! It works. This is an exact equation. It is exact. That's awesome. There is an f such that this equation is equals 0, so it's df equals 0. So now we know there's a df like that. So we know that q then is the partial derivative of f with respect to y, and p is the partial derivative of f with respect to x. All right, so now that we checked exact, let's move to the second step. Let's erase. Now that we've shown that this equation is an exact equation, then it's of the form df equals q dy plus p dx, right? Then we know that q is the derivative of f with respect to y, and p is the derivative of f with respect to x. So we know now that because of the previous result, that df dx is this, df dy is that one, so we integrate here with respect to y, and we integrate here with respect to x, and we get integrate with respect to y. This thing is y, so let me just write it. Okay, apologies for this disruption of the space-time continuum. I come from the future to prevent a mistake that I was about to make before it happened. So, I was about to go from this step to this one without carrying the 1. For some reason, I forgot, I just copied this and I wrote this without the 1. And of course, that will give you a different result. Now, that's the kind of mistake that won't take all the marks if you make it. That will take some marks. Like, you know, in my case, I'm taking myself some marks off for me. But still, it's essentially right if you do it right and it's consistent and the result is consistent with what you're getting. Now, that said, I came from the future to prevent the mistake from being made and then branching out a new parallel universe where the YouTube video is correct. Okay, so let's get to it. Remember, we're trying to obtain f of xy, that's our objective, by integrating the partial derivatives, right? By integrating the differential form. If we integrate the partial derivatives, we know that f is the integral with respect to y of partial f partial y, and f is also the integral with respect to x of partial f partial x. All right? Now, let's do the integral with respect to y first. Now, if we integrate with respect to y, we get that this integral is very easy. So this is y squared, this one is yx squared, the integral of these two, and the integral of 1 is just y. But of course, we know that the partial derivative with respect to y would have killed any terms that are only a function of x. So I need to add here a g of x, and that would be f of xy. All right? Again, if I take the partial derivative with respect to y of this, I obtain this expression. Wonderful. We do the same with x, right? We integrate the partial derivative of f with respect to x, and then we get that this is the integral of 2xy minus 9x squared dx. Now, if we do this integral, the first one is very easy, is x squared y. The second one is also very easy, so it's a 3 divided by 3, so it's 3 times x cubed. And of course, we realize that perhaps this partial derivative with respect to x could have killed any elements, any terms that are only functions of y. All right, so what we do here is to write a possible h of y, and that is f of xy. All right, now we compare the two expressions to determine the g of x and the h of y. So using a color code, we see that, okay, this term x squared y, it's here, so that's expected. And then we get a function of y here, that is this thing here, together with this thing here. This is a function of exclusively y, that's h of y. So directly, from comparison, we know that h of y, in this case, is y squared plus y. Notice in the alternate universe where I forgot this one, I would have only gotten y squared. All right, and then the same thing by comparison, we can see that the g of x, let's use a different color, the g of x is minus 3x cubed, right? So we see it's the function of only x that is here but not there, right? So g of x is minus 3x cubed. Wonderful. So I can write f of x, y. F of x, y is, completing the whole thing, is y squared plus y multiplied by x squared plus 1. And, you know, the plus 1 is taking common factor of this term that has a y, it's 1 times y, and this term that has an x squared. All right, and then plus the g of x, and the g of x is actually minus 3x cubed. All right, now this is not the solution, this is a step towards the solution. You wouldn't get full marks with this. The solution in implicit form would be given by, remember, the solution, integrating the differential form, if f of xy equals constant. Now, the solution in this case would be y squared plus y x squared plus 1 minus 3x cubed equals constant. That is the solution in implicit form. Now, if you cannot solve for y of x, that would be the solution. But if you can actually solve for y of x, you usually are expected to do it. So if I want to go complete here, I would use the quadratic formula. And I say, okay, so y of x is two branches, right? And it's like, okay, it's a quadratic equation. So let's identify, this is the b term, x squared plus 1, whatever multiplies y. So minus b, which is minus x squared plus 1, plus minus the square root of b squared, so x squared plus 1 squared, minus 4 times a, which is 1, c. And what is c here? What c is minus 3x cubed minus c, right? So we get here minus 4 times, or plus, right, because it's a minus, global minus, 4 times 3x cubed, right, plus c. All right, and then that's divided by 2a, which is 2. All right, so this is y of x. This would be the explicit solution. Usually arriving here is enough, but if you can, it's always good to be able to take one more step and solve for y of x. All right, so I hope that I changed the universe for the better, and I will leave you with past me in the previous video, now that the two realities have merged in a confluence and coalescence of alternate branchings and branching points of reality. Okay, I'll see you soon. All right, so I hope that it was clear enough. We can do more examples when we need if you want, but the mechanic is the same for all exact equations, and because the next topic we're going to see, it's called integrating factors for exact differential equations, we're going to see equations that can be transformed into exact, so we're going to keep practicing solving exact equations. So hopefully with these two and the ones that come in the next video, there will be plenty of practice for you to solve the assignments. And if not, you know what to do, right? Come, write down your questions, come to see me in our live sessions. All right, thank you very much. That's it for this video.